Gas and steam turbines represent the cornerstone of modern power generation technology, converting thermal energy into mechanical work that drives electrical generators. These sophisticated machines have evolved significantly since their inception in the late 19th century, now achieving remarkable efficiency levels and powering the majority of the world's electricity generation infrastructure. Steam turbine history. The steam turbine revolutionized power generation with its invention by Sir Charles Parsons in 1884. Parsons built the first practical steam turbine specifically designed to generate electricity, with early machines producing only a few kilowatts of power. By the early 1900s, technological advancements had enabled steam turbines to reach multi-megawatt scale, making them increasingly viable for industrial applications. The fundamental advantage of steam turbines over their predecessors, reciprocating steam engines, was their ability to operate at much higher speeds with greater efficiency and fewer moving parts. This led to steam turbines becoming the backbone of electrical generation in thermal stations, including coal-fired, nuclear, and gas-fired steam plants. The technology continued to evolve throughout the 20th century, with improvements in materials, blade design, and thermal efficiency. Gas turbine history. The concept of the gas turbine dates back to 1791 when John Barber patented the first design, though practical implementation would not come for more than a century. The 1930s marked a significant milestone when Brown Boveri built the first practical gas turbine for power generation, demonstrating the viability of the technology. The development accelerated dramatically during World War II with the invention of the first jet engine-based gas turbine for aviation by Frank Whittle in 1941. This breakthrough paved the way for post-war developments in heavy-duty industrial gas turbines designed specifically for power generation and mechanical drive applications. Today's modern F and H-class gas turbines represent the pinnacle of this evolution, with single-shaft units capable of exceeding 400 megawatts of power output and achieving remarkable efficiency levels, particularly in combined cycle configurations. Gas turbines, working principles and types. Working principle. The Brayton cycle. Gas turbines operate on the thermodynamic Brayton cycle, which consists of four main processes. 1. Compression. Ambient air is drawn into the compressor section, where it is pressurized through either axial or centrifugal compression stages. Modern axial compressors typically feature 10 to 20 stages and can achieve pressure ratios of 15 to 1 to 30 to 1. 2. Combustion. The compressed air enters the combustion chamber where fuel is burned at constant pressure. Modern combustors use advanced designs such as annular, canannular, or silo configurations, often incorporating dry low NOx, DLN, burners to minimize emissions. 3. Expansion. The hot, high-pressure combustion gases expand through the turbine section, where they drive the turbine blades, producing mechanical work. This section typically includes both high-pressure turbine, HPT, and low-pressure turbine, LPT, stages, with blades featuring sophisticated cooling technologies including internal cooling channels, film cooling, and thermal barrier coatings. For a power distribution, approximately one-third of the power generated by the turbine section is used to drive the compressor, while the remaining output is available for the generator or mechanical load. Major types of gas turbines. By application, aeroderivative gas turbines are adaptations of aircraft engines, featuring high efficiency, lightweight construction, and rapid startup capabilities. They are commonly used in LNG facilities, mechanical drive applications, and peaking power plants. Notable examples include the GE LM2500 and LM6000, Pratt & Whitney FT8, and Rolls-Royce Trent 60. Heavy-duty industrial gas turbines are designed for rugged, long-life operation with greater tolerance to fuel impurities. They are primarily used for baseload power generation and combined cycle applications. Leading models include GE Frame 6, Frame 9, and 9HA series, Siemens SGT5-8000H, and Mitsubishi M501G/M501J series. By fuel type, gas turbines can be classified by their fuel compatibility. Natural gas. the most common fuel source due to its availability and clean combustion characteristics. Liquid fuels, including diesel, Jet A, and kerosene. Dual fuel systems, capable of automatic switching between gas and liquid fuels. Hydrogen-burning turbines, an emerging technology for zero-carbon power generation. Syngas/biofuel capable, designed to operate on alternative fuel sources. Cycle variants, simple cycle gas turbines achieve 35 to 40% efficiency in heavy-duty applications and offer fast startup times, making them ideal for peaking power plants. Combined cycle, CCGT, systems utilize the exhaust heat, typically around 550 degrees Celsius, to generate steam for a steam turbine, achieving total efficiency levels of 60 to 64% with H-class turbines. CHP/cogeneration systems provide both electricity and useful heat to industrial users, achieving very high total thermal efficiency of 85 to 90%. Intercooled gas turbines remove heat between compressor stages to improve mass flow and efficiency, while recuperated gas turbines recover exhaust heat to preheat compressor air. Steam turbines, working principles and types. Working principle. The Rankine cycle. Steam turbines operate on the thermodynamic Rankine cycle, which involves the following processes. 1. Steam generation. A boiler or heat recovery steam generator, HRSG, produces high-pressure, high-temperature steam by heating water. 2. Expansion. The steam expands through the turbine blades, converting thermal energy into mechanical work. As the steam expands, its pressure and temperature decrease while its velocity increases. 3. Condensation. The exhaust steam is condensed back into water in a condenser, creating a vacuum that enhances the pressure drop across the turbine and improves efficiency. 4. Feedwater return. The condensed water, feedwater, is pumped back to the boiler at high pressure, completing the cycle. Types of steam turbines. Based on steam flow direction, impulse turbines utilize steam expansion in nozzles before it strikes the blades, converting pressure energy to kinetic energy in the nozzles rather than the blades. Common designs include Curtis stages, velocity compounding, and Rato stages, pressure compounding. Reaction turbines allow steam to expand as it passes through both stationary and moving blades, with both pressure and velocity dropping across the blade rows. Parsons' design is the classic example of a reaction turbine. Modern turbines typically employ a mixed impulse reaction design, combining the advantages of both types for optimal performance.